I'm asking him for the password, and he said, I'm forgetting my password.
I didn't want to change the
Who
password.
would ever
I
expect
was
to have so
confused.
much fun?
Sorry?
I said, who would ever expect to have so much fun in Quantum 2? We're having too much fun. We need to.
I tell you what, after Wade last spring,
Yeah.
there were a couple times I saw Wade and he was just like, I don't even know what's happening. I was like, oh wait, I just can't wait to get there.
Jacob, Kyle, help yourself to donut if you want.
I mean, I have one.
Sure. Thank you. Need a napkin for.
Here's the napkins.
Oh, okay. Cool.
Yeah, my only break to grab lunch was while you were doing that, so. I was like, I shall eat lunch. And then go teach. You ever see an interval that you just roll your eye at? You're like, why is the why? Why is that the result?
Yeah, I have no idea. Probably some limit. This makes me think of statistical mechanics.
It's probably a gamma function pops up somewhere. That's my explanation. One a month until we have to worry about midterms.
Spring break.
How about others?
Chandra is on the way.
I'm not sure. He's sick. So he gave me the notes. You
Chandra is
already
on the
passed,
way.
right? Let's wait.
Yeah.
Okay.
You can start.
We can start. Yeah. He set up and then we
Yeah.
We all wait for Jacob.
Yeah.
If I'm late, I'm not too late behind. Just give it
Oh,
a
he
sec.
saves me every time. If I fail, if I forgot what is mentioned in the class, I used to watch that video and that really saved me a lot.
I feel like I got lost at sea and I woke up on a shore and I don't know who I am.
Why do I not understand what you mean?
And I was given this like mountain of work that like I didn't know about and that's pretty much qualified.
Would you say the second semester has started off worse than the first semester
Well,
in terms of workload?
in terms of workload, yeah. Probably because all of the break was just looking forward to what was happening in January, and then whenever January ended, it's like, oh, there's all this stuff that needs to be done that happened in January.
I mean, third semester was worse for me, but I knew that and I saw it coming. It was like a truck and I just continued to stand in the road.
Yeah. Jacob's analogy, the shore. Kyle's analogy, the truck.
Kyle, just
Put
like
them
that-
together.
Kyle, just like that example in the lab that Anil made, the truck driver and the
And
boy on the bike.
They say the stupid boy.
Yeah.
Some superposition of those two states is graduate student experience.
Okay, you are ready?
Yes. We're ready.
Okay, ready. Eat some of a donut.
Yeah.
Okay.
Consolation prize.
Last time I mentioned the active rotation and passive rotation. I didn't draw this picture, so just try to remind you. I think you know that, right? What is active? So active means if there's a vector or some function like this function or some physical system, we rotate the vector system with a counterclockwise. So that is the rotation operator. And what happens to the system from R to R prime? So that is the active, that means we rotate the system, keep this coordinate same. Then this, so that is the expression say that this one is kind of a function set here. So that is system, we rotate system and go to another way after rotation, and then the components, in this case, components of this vector is relation, right? So this vector and this matrix, we are going to determine this one. Acting on this. Basic is that, okay, this one, and we have a new x vector and the component. It's equivalent, we keep here, we do not do this, but we rotate the x, the coordinates axis, right? So x go to x prime, y go to y prime, there is a negative opposite angle. So this is counterclockwise, this is clockwise, and you will see they are equivalent. So that is called the passive. And then the coordinates relation, the new coordinates components and the old one has this relation, and here it is negative, right? So then they get the same thing. Now, remember, come back to our question is how the rotation operator will act on the states or cat. So that is the definition. We introduce the rotation operator, apply to the cat. This we give a new one. And then in the position representation, we project to the position. Now this one is not this. This one is basically like the coordinates here, right? So we project any cat to this is vector R that set one is this one, right? So we just write down here, we place this set one cat like this. Now we look the left hand side. The left hand side is this wave function set one project to the R, the basis vector in the position representation. That is a function right here. I use function set one as function of R. Right hand side we already played last time. So this operator applied to the bra is equivalent to take this operator dagger inside and become a new bra. This is a bra, right? So now this is a function project to, not project to R, but project to the R dagger. That means make rotation. I think R dagger equal to, okay, I think you remember that is also equal to the inverse because it's a unitary operator, right? So to here, that means now this is function like this, they are equal, but now this is a function psi prime, a function R, but this is a function psi as a function of the variable is R dagger, that after rotation of this basis, or R inverse. So then you can see, if you look, this is active, right? We do the rotation on this property. So this is active representation. Then it is equivalent to, let me use the inverse because later we're going to use, equivalent to do not change the one function, right? But only change, rotate this axis with opposite. You will see later that the inverse is negative angle. So that is so far I think in the last class, right? Now this is for the how this rotation operator act on this cat or state. Next one, how about this rotation of the operator, right? We also ask ourselves, the operator is A, after the rotation, we'll go to A prime. So what's the relation between A and A prime? Let's do that. So in this case, we're going to use some of the relation here to prove. So first, we know A is operator, right? Applied to this side, that before rotation. That also gives us a new cat, we say set A, right? That is operator A act on this one of the eigenstates. The vector or cat, I gave a new one. Then suppose we have after rotation, so A prime is after rotation, the operator, then is we apply the psi prime because in after rotation, the function associated with that rotation. So that will give us psi prime A, right? One is in this old, this old before, that's the before after, right? Before rotation. This is after. Then the relation between psi prime and psi is rotation, right? Psi prime A is the rotation of on this psi A. So again, this is also before this is rotation. Follow this, and this is operator applied to the states or to the cat give us. So we are going to use those four relations to find what is the relation between A prime and A. Okay, now let's look at this one. Look at this one. So the left-hand side of A prime, psi prime, that is A prime. Now I'm going to use psi prime is here, right? So this R, the rotation on psi. That is left-hand side. When I say left-hand side is this equation, right? This equation. And the right-hand side. Right-hand side is this one. After A prime applied to the psi prime, it was psi A prime, right? Or psi prime A. So that is here. The relation between psi A and psi A prime is also before and after rotation, right? So that is right. Okay, I use this here. And then this one is here. Psi A is A operator applied psi, so that is A okay, now both sides be equal, right? So both sides equal, so now you can see here right-hand side we have this factor, right-hand side we have this factor, and the all applied to the cap, right? So we have the relation is A prime R in phi equal to R in phi A. So we have this relation. Then I multiply the R in inverse both sides, so you have prime is R in inverse. Right? Because Rn and R inverse multiplies got I, right? Identical. So now, this is how the operator transform after rotation. So that is this one. Okay. That is for the operator. You will see this like a sandwich, the old one, with rotation operator. So now we have the two. One is how the cat or the wave function rotate or change after the rotation, and how the operator. Now we are going to do is how to obtain this operator expression. We know the operator will make the change of operator and also the cap, but the rotation operator itself, how to express, right? We are going to write down this. In order to do that, so now first one, let's consider infinitesimal change. Infinitesimal rotation. And then we expand to the finite. Okay, so now that means we are going to find this one. This infinitesimal rotation. Okay. How to obtain this? Then now to obtain this, we are going to use the some representation, either matrix representation, position representation, or moment representation to help us to write down details, right? So now let's consider from the position representation, position representation. Okay, it's here. Yeah, this one. Position representation, wave function, or after rotation it change, but follow this, right? So now, because psi prime r equal to this one, right? So now equal to psi. Okay, let me write down first. Is since we take this, so it is rotation about this. Okay, now let's consider about z-axis. Let me going to consider infinitesimal rotation about z-axis. So here, that means we are going to first obtain this one, then we can extend to the general. So then, because if we want to rotate this function about the z-axis by infinitesimal rotation, so this is RZ instead here, right? And arbitrary rotation axis, now we just consider Z. So the index means around Z. Is this one, right? So that equal to this function here, that is RZ inverse, okay, delta phi on R, right? The inverse here, I think I can cover. Say we have, this is, let's consider this. This is a z-axis, right? X, y, or y, x. Okay. So if it's, if this is a rotate, this is the operator if we rotate the x-axis to around z-axis to the delta phi. But inverse, I'm going to say if I rotate by negative, so suppose you rotate with this delta phi, and then you take this counterclockwise, and then take the clockwise, you go back, right? So after that means this product give you no rotation, right? If no rotation, and by we know any rotation, any operator multiply its inverse is they are equal, right? So that means this two, the inverse definitely is nothing but just a negative angle. So here, I'm going to write down the next step is make the rotation negative, right? So from here to here, I just use this idea here. Negative is inverse. Then this inverse means what? Rotate about the z-axis. So you can see here, this is a psi function r in the spherical coordinates. That is r theta will not change, right? The change only is phi. So that is negative 35. Yeah. 5 plus the right? That is how we perform this infinitesimal association about the z-axis on the function. And what happened? We know it is only because this is passive. The reason why is from now on we use passive rotation because that convert to rotate only the basis vector over the, so that we can handle easily. So that is from here to here. Okay, now that's the first step. Then go to the next step. We have not yet find this location operator, so we need to go further. Try to find. We need to find this this one is original before rotation, right? So from the Taylor expansion. We are going to take the Taylor expansion because this rotation is infinitesimal rotation, right? So R theta phi is hit that one, right? So I can do this up to the first order, so that's approximately the original and plus first order plus first order, which is partial theta phi partial phi multiply this minus theta phi, right? Because we rotate the negative. So because it's small, so the high order term we can ignore. So that is this this expression, and then we can go to. I'm going to take this outside, so that is 1 minus equivalent to this. Now, okay. Now, if you remember, that is this one, right? So the side front, the left-hand side is equal to R around Z to form this infinitesimal transition. Rotation. So you can see here, this one, the same. Therefore, we can have the rotation operator along the z-axis. This infinitesimal rotation is 1 minus partial. That is operator. Familiar with this? LZ. Remember? Okay, now we write as a LZ. Let me write down here. Remember, LZ is minus IH bar partial phi, right? Spherical coordinates, chapter 6. So here, you just multiply IH bar divided by IH bar. So then it becomes minus I H bar LZ. Very good. So the rotation operator actually controlled by the angular momentum operator, and that makes sense here. If you remember in the theoretical mechanics, we have infinitesimal canonical transformation always has a generator. So this is a generator. So the rotation operator, generator of the rotation operator is angular momentum operator, right? Like this. Good. Okay. So from here, we write that is derived from infinitesimal rotation for only for x for the around the z, right? Special. So now we can extend to general. In general, so now consider we have arbitrary axis, and if we rotate this infinitesimal angle, so that is r. We can extend it very easily. This is about z, right? So if about this arbitrary, what does means? Inner product between axis and optical angular momentum, right? 1 minus this is n go over h bar, and here that is n, and now this is n hat, right? Unit vector. Very easily. And similarly, for along the x, just 1 minus I delta phi over h bar Lx, and y Ly. And this is in case if the rotation axis is x-axis or y. So here you see the angular momentum operator is a generator, which generate the rotation operator. Of course, we still deal with the infinitesimal, right? Not the finite. Before we go to the finite, let's look at the commutator relation between the operator, rotation operator. Let's see this one. R along the x, the rotation, and what is the commutation relation between the rotation along the y? Let's look at it. Okay. So that is, by definition, we realize Rx phi Ry phi minus Ry delta phi and Rx delta phi. That's the definition. Then each one, we know this expression in terms of this. This is an orbital angular momentum, right? So in this case, we consider in the real space, right, the rotation. We did not consider spin or arbitrary. So now here, let's consider this, because in real space rotation is corresponds to the orbital angular momentum. In general, we are going to do this in general. So now we substitute this into this, so that is Rx is 1 minus I delta phi over h bar Lx, and it's 1 minus I delta phi over h bar Ly minus 1 minus I delta phi h bar Ly, 1 minus I delta phi Lx. So let's first, here the first term, we have 4 terms, right? So 1 minus I delta phi over h bar, and this x, Lx plus Ly, right? And then the last one is the minus I, so this is plus become minus, right? I is in the delta phi square, h bar square. Okay, and this is a Lx first, right? Ly second. So that is the first. We have first 4 terms, and similarly, we have the second term have another 4 terms. 1 minus I delta phi over h bar Ly plus Lx, and minus delta square phi square h bar square Ly Lx. Now we can see some terms cancel. 1 cancel, this term cancels. The only remaining is the last, the second, the delta square phi, right? So that is okay. Minus, we have I. Okay. Minus delta square phi over h bar square. The first one is Lx, Ly minus Ly, Lx. That is commutation relation of Lx and Ly, right? So now minus delta phi square h bar square. Chapter 5. Who remember this? How much it is? By h bar Lz, right? So now we it is, okay, okay, let me run down here. So we have I H bar LZ, this part. Commutation relation between Lx, Ly is I H bar LZ. Then H bar cancelled. So we have I, so minus I delta square phi or H bar LZ. This means they are not commute each other. They are not zero, right? So that is the commutation relation. Or you can write, if you from here compare with this one, this is RZ delta phi, right? 1 minus. So then if they have if the angle is delta square phi, that is so here, this one is RZ delta square phi minus 1. So the commutator relation, rotation relation between x, y actually equal to this the rotation about the z-axis with the square. The angle is square, not this delta phi and minus 1. Similarly, the ry delta phi is you just like follow this the relation, right? Y and z. Here this is x, y, z. The y, z is be x, right? Follow this the last b minus delta square phi plus x. Sorry, no. Here, I just use the final, this one. So A H bar x.
Should that be phi
yeah.
squared?
Yes, this is square here. This is square, right?
Is the phi squared as well?
You mean no delta phi? I still infinitesimal change.
Okay, gotcha.
Yeah, phi square is a finite. Phi is finite. It's just considered. So that is.
So delta.
Yeah, delta. Yeah, okay. Over this one, over Rx. Then this Rz delta phi, Rx delta phi. We go to the Zx go to y, right? So that's minus I. There is y over y. This is just we can extend to the other direction. Okay, that is from this infinitesimal rotation. You have this general expression is no rotation plus sum of the infinitesimal items. Right? Now we go to the finite. Finite rotation. That is a general rotation. So now we have to extend the finite rotation. So finite rotation, say this is finite, not delta phi. So finite rotation about the given axis can we consider or view as a series of consecutive infinitesimal rotation, right? Do you agree? We just infinitesimal rotation continues over a series of these consecutive. So that means the rotation about them is still use let's consider z. From z and go to extend to the, so if along z now instead of infinitesimal finite, that be equal to I just around z take this series of infinitesimal rotation from an n series of n. Right, because it's around the same angle, so it's something like here I rotate this, but I can perform this one, right? Because the angle, the axis is the same, so I can rotate continuously, right? So if we have this, then that's each individual infinitesimal rotation. We already have the formula, so we just multiply those by n. If the n takes the larger, then this angle became a small, so that's close to this infinitesimal, right? So we can have this around z for finite. I can take n go to infinite, and then this rz to the nth power, right? And then n go to infinite. Rz is this one, right? Okay, just take z. So now let's 1 minus I. Okay, then first delta phi over h bar is z, right?
This is problem is really dumb. Why wouldn't it just be a sum of infinitesimal rotations instead of the product?
It is not sum. It is
Right.
it is like you rotate, and then after rotation, it is the operator sum is not. This is the operation. It is operation. Okay, then you have to sum like a shift translation. Okay, let me do this way. So suppose this is R, this R prime, right? Then this R double prime. So now from R, you take 1. Let me do this way. So from R, go to, let's say, R prime. That is what we did. We did is around Z. Say something like or whatever. Something like this, right? Now from R prime go to R double prime is RZ R prime, right?
Okay.
Then R prime is multiply, is not addition. R prime is here, right? And then you keep going.
Okay.
So that is product. Okay, now come back to here. Now I'm going to replace delta phi by phi. 1 minus is phi is n times delta phi, so delta phi is phi over n, right? And this formula you know. With some variable is when go to infinity, so that is exponential, right? This one. Okay. Hopefully this mathematically you know that is exponential minus I by h bar z. Okay, so now finally, let's that is let me write down again. LZ for finite angle rotation, that is exponential, not the 1 minus sum of infinitesimal change. So now minus I phi over h bar LZ. Again, here LZ is a generator. Then in general, now this is around Z, so we can extend to the arbitrary axis. In general, R about n axis for finite angle is simply we just replace the LZ by the inner product n unit vector with the element. Here, these two are generators. So this generator, whatever is infinitesimal rotation or finite rotation, yes, they all play an important role. So whatever happened, the rotation is always associated with a basic quantity that is angular momentum operator. that is very important. That is why we consider or focus on the rotation. We know that this rotation performs like this operation, but underlying physics is played by the angular momentum operator. All right, so now we derive the expression of here in general expression, but in general this is a rotation in space or spatial rotation. Right? We didn't consider spin, so now we are going to discuss. Can I erase this part? Now it's discussion. Some discussion to understand in details about this property of this rotation operator. So we are going to generalize to or so now we are going to consider spin over the total angular momentum. Even though we derive from this space, so because that is easier for us to derive, but this relation between this generator and the rotation operator can be extended to the in general. So in general, I'm going to write down here. If the system not only consider this orbital angular momentum, also the spin, so that is minus which down here is G. This is the first. You say you didn't prove. Yes, it is. In particular for spin, it's not easy to prove from here mathematically, but we can explain. Because whatever the spin of angular momentum, the orbital angular momentum, they all belong to the general angular momentum and have the similar behavior, right? So that is the extension. Total angular momentum here. So here, if the only consider spin, then you replace by spin. If the total includes the orbital and spin, you use the total. If only consider orbital, use orbital. So that is general. Okay. So that is generator here. Okay. There is generator of the total angular momentum. Second one, symmetry and conservation. So since we have physics here, the rotation operator has a direct relation with the angular momentum operator. Then that physics implies something we can analyze here. So if the system Hamiltonian commute with the rotation operator, what does it mean? Commute means H prime is a Hamiltonian after rotation, right? Remember the A prime equal to Rn by A, right? So here's H, Rn inverse, right? So because here, you see that is equal to, because if they are commute, right? So I can change the position. Right? What does it mean? If Hamiltonian commute with the rotation operator, it will invariant under rotation. And the rotation. Has a symmetry. Or the Hamiltonian definitely has a symmetry such that you rotate, yes, it will not change. So that is the first issue. If, so we have this first one. Second, do you agree? Because this one, the operator is still dominated or generated by this operator of angular momentum, right? So that is because Hamiltonian that is exponential. Any function operator, its commutator is controlled by operator itself, right? So this commutation relation is controlled by if Hamiltonian commute with G, then this commute. That makes sense? And now our initial conditions, this is this, right? This commute, that means imply this commute. So if this commute means what? Okay, I think this one maybe opposite. Like this one gave us Hamiltonian commute with this. That's the second. The third one. So that is the second. So from here, this is the first one, second, and third is, remember chapter 3, end of chapter 3, you can say this, discuss time evolution of expectation value of any operator equal to what? Remember that formula? Commutator relation between this G operator and Hamiltonian and partial derivative, right? Let me check right now. Remember this. 1 over H bar. It's the last semester. Plus partial G. Because this, right? This remember, right? Now if this commute, so that is, and we know G does not depend on time explicitly. So what that means, here, is conserved. So how important it is, so if we have discussed rotation operator, then let's consider the system Hamiltonian. If the Hamiltonian is invariant and rotation, immediately we have several information. The Hamiltonian commute with the associated with that rotation, maybe total general angular momentum, maybe orbital angular momentum, maybe speed. And then another implied is that generator is conserved. Right? That is very important physics here. So example, hydrogen atom, or just a center example. Hydrogen is one of the case, but all the central force or central potential system for central potential for a particle in central potential field, right? Then the Hamiltonian is the kinetic energy part. We know that does not depend on whatever rotation, is always invariant, right? Plus potential. So that is, because we only depend on the absolute value of R, but does not depend on orientation. So you rotate, it's a spherical symmetry, right? Because spherical symmetry, what do you rotate? Spacer, in the space. It will not change. It is in R under rotation. This rotation in space. So Hamiltonian. Now I'm going to is L. Is orbital angular momentum. not spin. I didn't say spin, right? Because here we didn't consider spin. So, and then, so immediately got this and also got this one. It's conserved. Constant. It's conserved. Okay, so this is a discuss second one. The third one we are going to discuss the property. So let's property, there are several properties, so now I'm going to separate, just focus on this four case of rotation operator. Okay, it is another topic. We introduce how the rotation operator acts on the cat on the operator. Then we discuss how to express the rotation operator in infinitesimal rotation and finite rotation. And this rotation can extend to the general as a sum of symmetry and conservation associated with the Hamiltonian invariant or not. Now we consider property in general. The first property is that the product of any two is still rotation. The product of any two rotation operator is another rotation operator. Mathematically, it means R about xn1 rotate y1, the product, right? Another rotation n2 by 2. Now, what is, so this product, it tells us it's be another rotation about another axis. Okay, here, if, let me just say that. So be careful here, I say this nx, so it's n1, maybe here, n2, maybe here, right? So this is a rotation. And it gave us replace equivalent to n3 about that n1, let's see this one. N3 is not simply this addition of two vectors. Be careful. And this one is also not addition of these two. We just say it will generate another rotation about another axis, but it's not simply addition. Let's be careful. In general, if about the same axis, say n1 and n1 and 2 all are z-axis, then they go to the z-axis. If these two are not the same axis, the n3 is not the same. Okay. Proof, right? So now we're going to prove why you say that is another rotation, because if the rotation operator, we know that is unitary operator, right? So we are going to prove this Rn3 is a unitary operator, then we know, yes, this product can generate another operator which is rotation. Because, let's look this, Rn3, let's say this dagger, right? If we are going to prove the dagger equal to inverse, then that is, right? That is satisfied rotation properties. So now, that is R3, phi 3 is this product, right? So that is R in 1, then 1, R in 2, by 2, dagger. And we know the product dagger is equal to the product dagger equal to the dagger product, but reverse, right? Position, so that equal to R2, Rn2, sorry. R2 dagger, Rn1, dagger, right? And then dagger, each one is a rotation operator. Because we say any two rotation operators, they are rotation operator. but we do not know the product if it is or not. So now, if this individual are rotation operator, they said they are unitary operator, right? So that's dagger equal to inverse. Then now we have a product of inverse that's to equal to the reverse product. I mean, not equal to, go back, equal to Rn1, Y1, R into this product inverse, right? Here's 2, 1, so the inverse be reverse, right? Okay. And this one is what? This is R3, Rn3, sorry, inverse. So now we found that R3 dagger, Rn3 dagger is equal to Rn3 inverse. So this product is another, is a rotation operator. That is first property. So now we don't vary. Then you may ask, how about product 3? Yes, product 2. All the products together. It will also, again, you don't vary. It must generate another rotation operator. But be careful that not simply addition here, right? So that is the first, and we are going to use this behavior when we derive the Euler rotation. Yes. So now, second property is mathematically this product is associated. Second one is N1, this is we have 3. Suppose we have 3 rotation operator. The product of 3. Okay, this product you can do first. We first rotate around N3 with angle phi 3 and then rotate with the product of this. So do not do N3 and N2 and then but N3 and then the product of these two. This product will become another rotation, right? That's equivalent to you do this first. That is associative. Associative property. So you can do this product first, and then do this one. So they are equivalent, but you cannot change the order, right? This is associative. Associative. Follow the associative law. Number 3. Okay. So if there's operator I, multiply this rotation operator and does not change itself, then okay, I is identity inverse. I rotation identity. Rotation. No rotation means, right? Or rotation is 0 angle. And that makes sense. That means if you find this operator follow this, this identity. So if we have the operator the inverse exists such that So if we have operator product and the product of these two just give us identity operator, then that is inverse of this equation and does not depend on the position. Here, we can prove that the inverse is nothing but just do the about the same axis, but the rotation is active. And we can prove that. Okay, prove because R in around the x n axis multiply R in rotation is an active angle that equal to, remember the R is exponential, right? Minus I in product is J and minus I minus I in J. Not equal to this, right? See the angle cancel. So it's equal to this. So that means equal to, since that means there exists inverse such that the product will give us the identity rotation. So we have this. So this one is equal to this one. And this one is nothing but it's a minus. I already show along the z-axis, right? So now this is arbitrary case. You can also prove that. So the later, when we deal with the inverse rotation, that is nothing but rotate with a negative angle. Right? This one actually already, it is unitary operator, right? Since we know it will not change its magnitude, it only change rotation. If it's a unitary, its dagger equal to its inverse, right? That is very important. And to prove this one is also very easy. Now we can prove R in dagger is exponential dagger. And dagger means this minus I become I. And in J dagger, right? But J is a Hermitian operator. J dagger equal to J itself. Negative angle, right? Because here is negative, so the plus, so that means correspond to the rotation negative. And from here, we know that negative is inverse. So its dagger is equal to its inverse. That is unitary operator. 6. Do not commute. R in operators do not commute. That's because the operator, the G components of G operator does not commute, right? So that means if we have n around n1 axis, that one R in 2, the general is not equal to 2, 2 R in 1. because N1, J, N2, J, not commute. For example, if N1 is along x-axis, N2 is along the y-axis, so this is J of x, J of y, do not commute, right? So therefore, the general is not commute. Be careful here. Last one, property is it will not change its norm of any inner product. Okay. So suppose we have two functions under the rotation of along n axis. We take the same rotation here. If then let's look at the inner product. After rotation, SB equal to the same. Before rotation, so now let's prove that. Here, that is when we take rotation, this is dagger, right? You remember? Right? This cat take bra. Remember this? Okay, so then here, that is this bra, and the cat is so this one, because the unitary operator is R inverse. And this one equal to here. I didn't do rotation. So don't worry that if after rotation we still can keep this inner product the same. Okay. So this is the general property we discussed. And now we go to the next one, is after oppression here. Minus I by HR in whatever, let's use J, I think, yeah, let's use still orbital. Let's try rotation. So use J is fine. Let's use J. General. Okay. So how to express this one in terms? So here, this is arbitrary. So we consider this rotation about the arbitrary and axis with gamma angle. How can we express this one in terms about z-axis, x-axis, y-axis? In that case, that means we can, because we know along the x, y, z is easier for us to express. So in terms of Lx, Ly, Lz, right? So that is general here. Then the question, can we? This is arbitrary. Can we express any rotation after rotation about the arbitrary axis in terms of this fixed same like along the x-axis, y, and z-axis? So that is we are going to Euler rotation. I'm going to introduce this Euler rotation, and think the Euler consider this way. So now I'm going to call it X, Y, Z, right? So now we here, let's see, now we are going to consider the rotation about n is gamma angle. So how to represent, or a kind of, that is the product, okay, I already knew. So a kind of a particular rotation about this arbitrary axis can be written as a product of rotation along x, y, z. That is the question, right? And the answer is yes. How to do that? So now let's think about this way. So now, suppose the z-axis and n form the plane, right? Z-axis and the n-axis can form the two-dimensional plane, right? So the two-dimensional plane project on x, y is here. This color. So this one is n project here. Then how to do it? I'm going to rotate about the z-axis by alpha angle. We do not know the alpha angle corresponds to this n vector project to x, y, z. So what happened is, let's first rotate alpha about z-axis. The goal is we are going to rotate such that now this is x prime. X prime. So now in such that x prime, z, and n in the same plane, and perpendicular to y prime. So y prime is there. So you see the, suppose y prime is here, right? After rotation. So this is alpha, right? Okay, so what happened now? This y prime is perpendicular to x prime, right? Perpendicular to n, right? Because it's perpendicular to this z, n, and x prime plane. Y is here. This is plane, right? That is we rotate. That is first. Then after that second, I'm going to rotate y about y prime about beta angle. So then the z will go to same direction as n. So now it is z double prime. And of course, if you consider x double prime is here, right? So I don't want, this is not interesting. You just focus on z. So when this is rotate, and beta about y prime axis. Then such that the goal is make the z go to z prime, which is parallel to the n. Okay, now the third one, rotate gamma about z double prime axis, and that's equal to about n, right? Because z double prime parallel to z. So that means a rotation about the n after axis with an angle gamma is equivalent to proceed 3 steps. First, I'm going to rotate about z with angle alpha. Then I'm about y prime with beta. The third one, let's go to this. Do you agree? Oh, okay. So if you agree this picture or step, then we are going to realize this by this one is a product of about z double prime gamma. Okay, I just give you here and later next week. So the second one is about y prime beta, right? The first one is about z alpha. So I perform 3 rotations. First, rotate about z alpha, then about y prime beta, then y prime beta, so z go to z double prime, which is along z around the n and gamma. That is. And then, but this is a different axis. So we are going to replace y prime, z prime in terms of x, y, z in the same axis. That is the Euler rotation. Okay. You both have not take this homework 2. Okay, your homework 1. How about you? You done? Almost. Okay.
I'm on vacation.
Or tomorrow, it's
Yeah.
something, okay. You can either put in my mailbox or,
Thank you.
yeah. Let's see, only 3, yeah, 1, 2, yeah. You have this? Okay.
Maybe it's the nasty part that I just feel like. And I left my umbrella in the car, which means 100% likelihood it's going to be raining when Stat Mac is, or ENM is over. Because there's no way I make it to the car
Maybe
dry.
rain later afternoon?
I
Or
guarantee,
evening?
because I didn't bring my umbrella. That's why it's going to rain.
That's your logic.
Yes. I'm convinced.
Okay.
That's my logic.
Actually, that is Zane.
Yeah, take another one.
I just made sure to offer his donuts to you.
Thank you, Kyle. You're doing your job.
Well, good. Then I'll eat another donut.
Dr. Yu,
Yes.
what does that bottom one say? The from.
Allow rotate about the double prime here with gamma angle gamma. And this is because the double prime parallel to this end, the one along the end. is the gamma.
Thanks, Jacob.
Oh,